Today we'll talk about functions in Julia, and we'll start by defining what is a function. A function is a block of code that performs a specific task. It takes some input, processes it, and returns some output. Functions are a fundamental building block of programming, and they are used to organize code into reusable, modular pieces. And this is why functions are so important in programming, because they allow us to write code that is more readable, reusable, and maintainable. And by breaking our code into smaller self-contained pieces, we can make it easier to understand and debug, and we can also reuse the same function in multiple places in our code base, which saves us time and effort. To define a function in Julia, we start by the function keyword. Then we put the function name and then the different arguments that we want to use inside the functions. Then we put the actual code of the function and we end the function with the end keyword. So let's say we want to invest 10,000 euros on an account providing a 10% annual interest rate. And the question now is, how much will we get after 10 years? Well, we can simply compute it with the following formula. So what we want to compute is FV, the future value. And to compute it, we start with PV, the present value, an annual rate R, and the number of years N. Now we can define a function that will implement the formula for calculating the future value of our investment as shown here. So we start by the function keyword, then define the function name, future value, and we pass to the function three different arguments, investment, rate, and years. And inside the function body, we have the actual equation, the investment times 1 plus the rate to the power of the number of years. And to use the function, we just have to call it by its name, followed by the different values that we want to use for the different arguments. So for example, here we want to compute the future value of a 10,000 euro investment at a 10% rate in 10 years. And thanks to the magic of compound interest, we would have around 26k euro. Julia has several ways to define and write functions. The function definition that we just saw is defined as the long form. We have here a very simple example with a function named f that takes two arguments and just adds them. So this is the long form, but we could also write the function like this. And what we have here is the short form. And as you can see here, the short form drops the function and the end keyword and use an equal sign to put everything in one line. A third form for the function definition would be the anonymous function. In this form, we drop the name of the function and replace the equal sign by an arrow. This third form is a little bit special and is usually used as arguments to other functions, such as the map function. And map is just applying a function to a list of values. So sometimes functions don't even need a name. So in summary, we have three different forms for defining functions: the long form, the short form, and the anonymous function. Now I told you that functions take arguments. What we saw earlier is a function defined with positional arguments. And what we mean by positional arguments is that the first value will be given to the first argument, the second value to the second argument, and the third value to the third argument. But we can also pass arguments by keywords. If you add a semicolon before some arguments, you would then define all the following arguments as keyword arguments. And now when we call the function, we have to name the argument explicitly. And this way, the position of the arguments in the function call doesn't matter anymore. We can also put default values to some arguments. So for example, if we compute very often the future value for 10 years, it would make sense to use 10 as a default value for the years. And this way, the next time you want to compute the future value just for 10 years, you can just drop the years argument. A pretty nice usage of default values is when we mix positional arguments with keyword arguments. So for example, here we will define rate and years as keyword arguments with default values. And this way, when we call the function, we can give the investment as the positional argument, so the first argument, we say 10,000 euros. And if we want to keep the default value for the rate, 0.15, we can just change the year's value. There is also a way to provide any number of arguments to a function. And these functions are called vararg functions because they allow for a variable number of arguments to be passed in. Writing a vararg function is very simple. You just have to add an ellipsis after the argument name. The ellipsis is the three dots after the x in this example function. And thanks to the ellipsis, we can pass any number of arguments to some all. So in our example here, we provide three numbers, 1, 2, and 3, and the function iterates over all numbers and sums them up. We already talked about anonymous functions previously. They are usually used in other functions that take functions as arguments. So for example here, the map function takes a function as its first argument and applies it over all elements of the second argument. So with this syntax, it's pretty clear that we apply the sin function over 1, 2, and 3. But sometimes the function that we want to apply to our collection is a little bit more complex. So for For example, here we use map to apply a function that takes 2 arguments over 2 collections. And while the code is still readable here, it's starting to get cluttered. So I let you imagine what happens if the function is a little bit more complex. A nice solution then is to use the do block syntax. The do block syntax can be applied to any function that takes a function as its first argument. And instead of providing an anonymous function as the first argument, we provide the argument values still inside the function call, here 123 and 322, and use a do block to provide the anonymous function arguments, here we have x and y, followed by the actual code of the function between the do and end keywords. This way, the code is more readable. By default, functions return the last executed statement. So in this example, the result of this computation will be returned. And depending on the source, it can be considered a good practice to explicitly return the last value for a long-form function definition. So I would say it's up to you to define whether you always want to use the return statement or not. The important thing is to determine what you prefer and stick to it. However, there are 2 cases where the return statement is very nice to use. The first case is when you want to return a value early in the function to avoid computing unnecessary code. Our example function starts by testing if the value of y is below the value of x and returns x if that is the case. There is no need to execute the last portion of the function that only runs when y is above x. The second is when we mutate the value of a variable and want to return its value explicitly. In this case, it is not necessary to use the return statement, but it makes the code more readable. And the last nice thing I wanted to talk about is function broadcasting. Imagine that you have a vector of 3 values and you want to apply the sin function for each element. What you would be tempted to do is to pass a directly to the sin function. Unfortunately, Julia doesn't like it and returns an error. The error is pretty explicit. Julia says there is no method to compute sin over vectors. This can be a little bit overwhelming at first if you come from R or Python, where those simple functions are vectorized by default. This is because they tend to avoid for loops as much as possible because they are slow in those languages. But not in Julia. So the Julia community prefers to be explicit regarding iteration over collections. Usually, if you want to apply a function over a collection, you can write a for loop or an array comprehension. But you can also use broadcasting. Broadcasting simply applies a function over all elements of a collection, just by adding a dot after the function name or before if it is an operator. And that's it for this tutorial on functions in Julia. We've learned what functions are, why they're important, and how to use them. I hope you found this tutorial helpful and informative. As always, you can find the Pluto Notebook of this tutorial on the GitHub repository at this link. I'll put it in the description too. Oh, and this time I have a little surprise for you. I made a website out of the Pluto Notebooks, so there is no need to execute them to see their static content. And this is thanks to the template provided by Fabian Gremel from the Computational Thinking course at MIT. Okay, and that's it. Remember that this video is part of a playlist. Thank you for watching and see you next time.